Right, the goal of this video is to introduce a description of the symbol synchronization problem that we're going to try to solve next. Okay, so far we've looked at using adaptive techniques for gain control. We've done that. We saw that we needed to do that to get the symbol sizes correct. We need that when we downsample we get the correct values of the symbols, the threes, the ones, minus ones, and minus threes. The other thing that we took a look at was carrier synchronization. We knew, or we found, that if you don't have the transmitter carrier oscillator having the same frequency as the receiver carrier oscillator, you would get problems when you demodulate. And we came up with an algorithm. We looked at the Costas algorithm for solving this problem. Okay, so what I want to do next is describe what the symbol synchronization problem is. It's a different type of synchronization problem that we haven't talked about yet. It might have occurred to you that this would be a problem. It might not have. All right, so let's just talk about that for now. So the next step is to answer the question, why symbol synchronization? Okay, so to do that, I'm going to start with our friend the triangle waveform because it's easier to draw sketches of the triangle waveform. So I've already drawn one here. Let's say this is the signal that we receive at the receiver. Okay, so this particular shape was transmitted. We assume we did any kind of carrier synchronization, gain control, all those kind of things. So we get this valid looking received signal that has triangle pulses. So we see in the first symbol interval here I've got an amplitude of a 3. The second symbol interval I have an amplitude of 1. And for the third symbol interval I have showing up here a -3. Okay, so you get the idea. We've done this many times. Okay, so one of the things we've looked at is doing eye diagrams, and if, for example, our received signal is delayed, all right, if our received signal is delayed, then the optimal downsampling time would be in here, okay? So this would be at 6, and then, the symbol interval in this case, I've drawn it according to this grid, so it's m is equal to 8. Okay, 6 plus 8, we'd have something here at 14 and 22. All right, so those are the optimal downsampling times. Okay, that's well and good. Those turned out to be integer values. Okay, but if you think about it, there's no reason that you're going to end up with exactly integer values for delay. So what would happen, for example, if ended up receiving this waveform? Okay, so you see here I'm right between grid points. Here's one side of the grid, here's the other side of the grid. This is 6 and this is 7, so the optimal downsampling time is n equals 6.5, a fractional sample value. All right, so how are we going to handle that? And if you think about it, yeah, that's going to be a problem. And in fact, there's no reason to assume that the symbol intervals are going to be exactly the same between transmitter and receiver. All right, so you know how digital systems work. You have a system clock. All right, so even if you're operating at what's supposed to be nominally the same system clock, if there's some slight differences between the frequency of the system clock, then you're going to generate actually different symbol intervals. All right, they might be really, really close in time, but if you're communicating quickly, these differences would add up. All right, so what we're going to do next is we're going to take a look at MATLAB and how we would model fractional sample delay. I'm going to show you a quick video on that. We'll probably actually do 2 videos on this. One where we just have a fixed offset. That's what I've done here. I offset the waveform by some possibly fractional sample value. All right, so we're assuming the symbol interval is exactly right, but We don't know exactly this delay, and it could be a fractional delay. All right, so that's the first thing we're going to take a look at with MATLAB.
The MATLAB code that I'm using to show you how to model the situation where you might have a fractional delay between the transmitted signal and the received signal. Okay, by fractional delay, I mean the actual delay occurs at some value that's between samples. Okay, and so we're going to start with some of our usual parameters. M is going to be 10, and then sims. If you recall sims, let me drag this into the picture here. Sims is the number of symbol intervals that are to the left of the main pulse in a square root raised cosine pulse, and the number of symbol intervals that extend back to the right. Okay, so the total pulse length extends over 2 times sims intervals. Okay, all right, so there's that. We're going to use beta equal 2. Beta is the roll-off factor. All right, so this is the ideal pulse shape. This is what we would know. You know, if we were doing things ideally, we would have 0 offset. This is the offset parameter on a square root raised cosine pulse. And we would have these sample values, and all would be good. All right. This is the impulse response for pulse shape filtering. So what we know is that with pulse shape filtering, we flip the pulse shape, call that the impulse response, and then we might have to scale it. We do have to scale it, as a matter of fact. All right, so what I do is I calculate the maximum of the convolved shapes. That will give me the peak that's coming out of the filtering step. And then I take the impulse response and I divide it by that scale factor. All right, so what that would do for me is that if I had a pulse shape with a maximum peak of 1, all right, after I send it and do the receive filtering, the peak is also going to stay at 1. All right, it's not going to add any gain to the signal just due to the filtering. Okay, so we talked about that in the previous video as well. All right, so our usual steps: generate some PAM signals. I'm just going to, let's make 1,000 symbols to make the plot look a little more dense. Okay, we know our upsample factor. I don't need that again, so I'm going to delete it. All right, we generate the pulse. Okay, so here's a different step. All right, before I had an ideal pulse with 0 offset. Okay, now I'm generating a pulse with an offset of 0.5 samples. Okay, not a whole sample, a fractional sample of an offset. Okay, from there, and you can imagine how that would work. All I'm doing is I'm sampling this square root raised cosine pulse instead of sampling at equally spaced intervals starting at 0 going in both directions by sims. I start at t equal 0.5, you know, 0.5 of a sample, and I sample the waveform. You know, the time domain waveform, I know the function of time. I can just simply plug in and get these pulse values for any offset value that I want. Okay, so I have the offset pulse, I filter, and that generates the signal. This will naturally have a delay in it of 0.5. All right. Now, I don't know that delay. In general, this is a model. In general, what would happen in reality is I don't know what delay is going to be generated between the transmitter and the receiver. Okay, so later on, when I do receive filtering, so let me slide this down. When I do receive filtering, I use H, the H that I calculated from the ideal pulse shape. Okay, so that's going to be used in the receive filter. All right, so this is all set up with the model. The model has some delay built in it, a fractional sample delay. Okay, when I run this, it will generate a couple of things that I wanted to talk about. Okay, so the first step, this actually relates back to pulse shaping. All right, so the first of these plots is an eye diagram, and the eye is open the widest at, you can kind of zoom in here and tell the eye is open widest at about 10.5. Okay, so a fractional sample value, not at 10, not at 11, at 10.5 is where it's open the widest. This is the case where we don't have receive filtering. And so I'm looking at this and I realize this is noise free. This is all, deterministic stuff. This is inner symbol interference that comes from using a square root raised cosine pulse without filtering. Okay, so here's a point I want you to remember for like multiple choice quizzes and final exams. You can start with a pulse that's not Nyquist. Right? This pulse shape is not Nyquist. Right? At the optimal sampling time, there's inner symbol interference. It is not a Nyquist pulse. Okay? Once you do the filtering is designed, it's square root raised cosine pulse. They took the square root in the frequency domain so that the ultimate result after filtering would be a Nyquist pulse. All right, so this pulse here, after filtering, is a Nyquist pulse. All right, so you see here, Nyquist simply means at the optimal downsampling time, we don't get any inner symbol interference. Okay, I'm going to zoom on this a little bit. Okay, so these are essentially lined up perfectly with no inner symbol interference. Keep in mind, this is a transient response from the fact that we have a symbol interval that extends back before the symbol actually occurs. Remember, look at the pulse shape here. The pulse shape occurs at 0. The symbol interval starts before that. Okay. Okay, so this part is a transient response. All right, so ignore that, and you can see 0 inner symbol interference. Okay. The other thing to notice, and that's the thing we're trying to model here, is that the optimal downsampling time is at 10.5. Okay, if you zoom in on this, if you run this code, zoom in, 10.5 is where we would optimally downsample that, not at 10, not at 11, it happens at a fractional value.
Okay, as a quick summary, we use the square root raised cosine pulse to generate pulse shapes in this example. And I mentioned there's a mathematical expression for this. I Googled that and found this on a wiki page. And you can see it's a pretty complex expression, and that's why we don't just write it down in general because it takes too long to write down. All right, but if you think about it here, what we're doing is we're sampling this as a function of time, and one of the things that we get from this is the ability to add the offset value that shows up in the TB MATLAB code that does square root raised cosine pulses. All right, here's a picture of a raised cosine pulse, so hopefully that's in your head that when you have beta equals 0, that looks like a sinc function with the larger tails. With beta equal 1, it rolls off. It's the blue line that rolls off really quickly, and there's less susceptibility to inner symbol interference. All right, so that's just sort of a review of pulse shape theory. All right, so what I wanted you to come away with in this video is that, number one, we can model having any type of delay that we want. We're not constrained to just sample times. Okay, so we use this offset parameter in the square root raised cosine pulse function to allow us to do this modeling. Okay, the other thing that is a takeaway from this video is that when we start with square root raised cosine pulses at the transmitter side, these are not Nyquist pulses. All right, so if you remember that graph without filtering, you get inner symbol interference at the optimal downsampling times on a square root raised cosine pulse. However, if you take a square root raised cosine pulse and you apply the matched filter, right, optimal filtering, the resulting waveform is Nyquist, and there won't be inner symbol interference all other things being equal. Okay, so those are the main takeaways from this video. Please watch it and answer the quiz.